let's do a quiz. And I think it would be a good idea to do a little review quiz here. So let's do something that maybe you haven't seen in a while. Potential difference. Potential difference. Okay, you have locations A, B, and C on this triangle here. So here's A, here's B, here's C. So positive Y is that way, positive X is that way, usual coordinate system. And throughout this entire region, everywhere in space here, there's a net electric field, 3 times 10 to the 4th, 0, 0 newtons per coulomb. Okay. What's the potential difference VC minus VA? VC minus VA. So here's C up here, here's A down here. What is that potential difference? Okay, 72% of us say answer number 3, negative 210 volts. That is correct. That is correct. So what are the big mistakes? One is sign. Okay, so you got to be careful of sign. So positive 210. The other big distractor was this 258, which I believe people got by finding this hypotenuse, right, and multiplying by the field. Well, it just doesn't work that way, right? The potential difference is a dot product. So we have VC minus VA, and we're giving you the most exact definition is the integral of E dot dl, negative, in this case it would be from A to C, E dot dl, but the electric field is uniform here, so this boils down to just negative E dot delta L, okay? So you have negative 3 times 10 to the 4th, 0, 0, dotted with a path that is going to be going from A to C, right? And so that path has an X component of positive 7 times 10 to the minus 3 meters, and a Y component of positive 5 times 10 to the minus 3 meters, comma 0. And when you take the dot product, does the Y component matter? The Y component doesn't matter, right? Only the X components matter. So we get negative 3 times 10 to the 4th times positive 7 times 10 to the minus 3, and that gives you negative 210 volts, okay? Or alternatively, I mean, it's mathematically works out to be the same, but you can conceptually think of this as you go from A to B, and that would give you a potential difference of negative 210. And if you go from B to C, that should give you a potential difference of 0 because it's perpendicular. The path would be perpendicular to the field if you go from B to C. And going from A to B to C or going from A to C, it doesn't matter, right? Path independence says we can choose any path we want. So be careful of that. It's not just field times distance. It's the dot product of the electric field with the path vector and the if your path and field are parallel, then you just multiply them together. But if the path and the field are perpendicular, you get 0 for the potential difference. Okay? Okay, good. Most people seem to remember what they did last week, so that's good to see. All right. Let us go back to then Biot-Savart Law. And I was debating whether to go through this derivation, but I think I'll do it just to show it. And the derivation I'm talking about is we talked at the very end of class last time about a long straight wire. So this is a wire, and it has some conventional current running through it in that direction, call it capital I. And the wire is on the x-axis, so this is the y-axis, this is x. And we want to find the magnetic field at an observation location of 0, y, 0. And here's a little segment of wire that has a length delta L. And the position is x, 0, 0. And then this delta L vector, which is a vector pointing in the direction of the conventional current, we'll just call the length of that vector delta x, and then it's in the x direction, so it's delta x 0, 0. Okay? So I'm just going to show an example of using this Biot-Savart law, which is the delta B is equal to mu naught over 4 pi I delta L cross r hat over r squared. We talked about what we're doing. We showed this as a computer program last time, how to do it numerically, where you're adding up the magnetic field due to each individual segment and then summing them up. Okay, so it's much like what we did with electric fields due to a charge distribution. You break it up into pieces and you add up the electric field due to each piece, and then you use superposition to find the net electric field. Do the same thing here. So we start with a typical piece and we find the r vector from source to observation location for that piece. So that r vector is pointing from here to here. And r is going to be final minus initial, 0, y, 0, minus x, 0, 0. So r is going to be then negative x, y, 0. We need to find the magnitude of that. That's just going to be square root of x squared plus y squared. R hat is r over the magnitude. We have negative x, y, 0 over square root x squared plus y squared. And by the way, this derivation is in the book, so if you want to take notes, that's fine, but if you'd rather just sort of follow along, that's okay too. We need to do the cross product here. Okay, so we found r hat and we found r. Now we want to think about this cross product delta L cross r hat. So we have delta L cross r hat is going to be delta x 0, 0 crossed with negative x, y, 0 divided by this magnitude. And already we know what's the direction going to be. Before we even work this out, the direction is going to be what? Out of the board, right? Right-hand rule. Fingers in the direction of delta L. Curl them towards r hat. Thumb points out. So we know that we're just going to get a z component, and that delta B is pointing out. Okay. And there's a number of different ways you can calculate the cross product, but the sort of longhand form of doing a cross product, if you have A cross B, and I'm not sure how many of you have seen this before, but you have A, if you want the x component, you have AYBZ minus AZBY, comma, the y component would be AZBX minus AXBZ, and then the z component is AXBY minus AYBX. How many people have seen that before? Okay, some of you have seen that before. You can get this from doing a determinant. Some of you may have seen a determinant method of doing a cross product in a calculus class, but it works out to be that. All we care about is the z component because we know x and y are going to be 0. So the z component of this cross product, and I'll write it as delta L cross r hat z component. Well, let me bring this 1 over the magnitude out. It's just a factor that multiplies the whole thing. Okay, so that's still here. And I'm taking the cross product of x0, delta x 0, 0 with negative x, y, 0. So I have the x component of the first vector, so that's going to be delta x. I have the y component of the second vector, which is y, minus the y component of the first vector, which is 0, and I'm done. Okay, so that's the z component of that cross product. So when I plug that back into here, and again, I'm just looking at the z component of delta B, I get mu naught over 4 pi I have capital I have delta x, I have y, and I'm dividing that by, oh, well, first of all, I also have this thing, square root of x squared plus y squared. And then I have another r squared factor here, so I have square root of x squared plus y squared squared, so that's just x squared plus y squared. And then I combine the denominator. I have I delta x y over x squared plus y squared to the 3 halves. Okay? Once you've got this delta b, and notice it's in terms of, again, we're going to do an integral, so we're going to sum up all these delta b's, or take an integral of the db's if we go to very small pieces. Then what's our integration variable? What are we summing over? What's changing as we move from one segment to another? X, right? X is changing. So we've got everything in terms of the integration variable and constant, so that's okay. And x is running from where to where? Well, x is running from, let's say, for a segment that has a length of L, x is going from negative L over 2 to positive L over 2. And that gives, if we do this integral from negative L over 2 to positive L over 2, of mu naught over 4 pi I y dx over x squared plus y squared. Mu naught over 4 pi I and y are all constant, so it just becomes an integral of dx over not square root, x squared plus y squared to the 3 halves. X squared plus y squared to the 3 halves. When you do that integral, you will get the following, and you either look it up in a table or plug it into Mathematica or something like that, and you get the following result. The magnitude of the z component is going to be mu naught for 4 pi L, the length of the wire, times I over the y times the square root of y squared plus L over 2 squared. Okay? And then because, okay, so that's a result for the magnetic field of a wire of length L on the perpendicular center, or what we want to call this, perpendicular bisector, right? A line going through the middle of the wire and the distance point perpendicular distance away of y. Okay, but again, we usually call that distance r as usual, so I just make a change in substitution. So I'm going to call this r instead of the vector r now, and so this becomes r, and this becomes r squared. Okay. So it's another result, but it's coming from just applying this summation due to the Biot-Savart law. And then I think at in the very end of class last time we said if you have a case where the wire is very long and L is much, much bigger than R, and so what this boils down to be is this. You end up with, let me erase this over here. You have mu naught over 4 pi. You have L times I, and then you have R. So you have square root of L over 2 squared, which just becomes L over 2. And then the L cancels out, and the 2 goes upstairs, and so we have mu naught over 4 pi 2I over R is the magnetic field for a long straight wire. Okay, this is a case where L is much, much bigger than the distance away. from the wire. Okay. So it's kind of a nice expression. Kind of, again, it's an approximation, but it's a useful approximation, and we get this 1 over r distance dependence similar to the 1 over r distance dependence for a long charge rod, for the electric field of a long charge rod. Okay. Questions here? This just, it's a derivation, just going through the machinery of getting this result. You can review it in the book, but I just wanted to show where this comes from as just an example.